So I've put together a bit of a talk today about dual frame imaging, particularly with the iStar sCMOS. So just to give you a bit of an overview of what I'm going to talk about today. So first we're going to talk a bit about dual frame PIV imaging, some of the key component considerations within the camera that we need to think about when we're doing this sort of application. Then I want to talk really in detail about how PIV works, sort of on a basic level, but then going into sort of how it works on the sensor level, and then the implications then are in terms of how we time our experiments and how we time when we take our images, because that's all very much linked to how the sensor operates. And then I'll talk a little bit about some of the advantages of intensified PIV, some of the phosphor considerations with PIV mode, and PIV experimental setup considerations. I should say that I use the term PIV mode because that's what we set it in the software. It's the same as dual frame imaging, but for the purposes of this talk, I'll refer to it as PIV, just so I'm sort of a bit more consistent, but it's the same thing. So why we might want to do dual frame or PIV imaging, it's simply so we can take two images exceptionally close together in time. And there might be a few applications where you want to do this, such as if you're doing some kind of planar laser induced fluorescence and you want to maybe take a background image really quickly close to your main image so you can subtract some kind of background noise or source, or if you're doing particle imaging for symmetry, hence PIV, in 2D or 3D, and this then lets you view the movement of particles or fluids or plasmas or liquids or gases. Yeah, split second. I say split seconds, but is it smaller than a split second? Very close together, and then you can determine the direction of flow or motion within whatever it is you're observing. And these are sort of two of the main applications for this. There are a few others, and in terms of the sort of key component considerations of your camera, I mean, you have all the similar components. We've gone over these in previous talks, but I want to focus today in particular about the things which are particularly sort of importance when you're doing PIV. So that's the photocathode, the phosphor that you choose, and the sensor choice that you have. Because basically how PIV fundamentally works is you have sort of two choices. You can, in the context of sCMOS anyway, in that you can do sCMOS PIV, where you have, say, you have some form of event or two events that you want to look at that are very close together in time. You can take a, you can set your sensor up so you take a really small, take two images with a really short interframe gap, and this works quite well for many applications where your event is limited to a very small period of time and you don't have too much background noise or background light. But one of the great things about like a device such as iStar sCMOS, for instance, is that you can use it for intensified sCMOS PIV. So you have your same event with, or two events that are happening close together in time, or two things you want to observe close together in time. But in addition to having the sensor set up in this way, you can also use a photocathode gate. And this has several advantages, which I'll sort of talk about now. So, as I said before, you can reject stray background light. I was looking for a good picture to sort of point out the benefits of this, but this one sort of gave a bit of an example of, you can see the main thing you want to look at much better if you can get rid of anything that's in the background that's, reducing the quality of your image. And if you have an intensified camera, you can then access different time domains with PIV, because you can sort of exceed what the camera is capable of clearly defining. So like 2 microseconds in the case of our sort of Xyla camera, which for instance you could use for PIV, but you can take it down to the nanosecond time scale and have images really close together in time. And I'll talk a little bit about how you can do that in a minute. And also, if you have an intensified camera set up for that's suitable for PIV, you can also then use the same camera for a variety of other applications should you wish to, such as, PLIF or spectroscopy, or, you could take a camera like this and then use it for various other things as well. So it's quite a versatile instrument. So how does PIV mode actually work physically on an sCMOS sensor? And I'm sure you've all seen this diagram that I've shown you a few times before of, the layout of an sCMOS sensor, where you have this array of photodiodes and amplifiers and pixels that you have. But, and I'd say this because it's sort of important for understanding the timing, is if we take a little bit of a deep dive into what's actually going on the pixel, and I'm no engineer, so bear with me here, but if you have the sort of the diagram of the pixel circuitry, what you have is you have this pinned photodiode, which is effectively your pixel, and you have also this point here, which is your sense node, and between these you have a gate. And what you can do, what you sort of do in PIV mode is you set it up so you expose your photodiode or your pixel for whatever time frame it is you want. And then what you do is you open this gate so you can transfer charge from your pixel into this sense node. And then what you can do is you can then shut this gate, and then you're effectively immediately, I say immediately because it's not really immediate, and I'll elaborate on that in a second. You then start your next frame as quickly as possible because you literally just have the time it takes this particular pixel to empty into this sense node. And then while this pixel is exposing, you can then open these other gates to then read out your previous image while you're exposing your next image, and then you get like good uptime, and that allows you to take these two frames really, really close together in time. Now, the reason I show you all this, though, is because though I say immediately, it's not actually immediate. There is a physical time constraint for these things to actually physically happen. And so what it actually looks like in reality is, if you imagine this is the edges of your two image frames in time, we say there's a 2 microsecond gap between this image frame 1 and this image frame 2. But reality is not quite as black and white as that. And what you actually get is you get this sort of, there's a point in time, but about 100 to 300 nanoseconds long, where you have a transition where simultaneously your pixel is absorbing light that is contributing to image frame 1, but also absorbing light that is contributing to image frame 2. And it's this transition that you notice is actually much shorter than this 2 microsecond gap that can allow you to take images that are, say, 100 nanoseconds apart, 300 nanoseconds apart. But there's a certain amount of sort of crosstalk that can come with this. So one thing you can do with this interframe gap, because this might happen here, it might happen slightly to the left, slightly to the right, so it can be quite hard to not know exactly where it's occurring within a particular image sensor, is you could have a laser set up such that you move it forward in time and you measure the intensity across your two frames, and you can actually then quite easy, well, relatively easily observe this sort of interframe gap and the sort of different intensities that you experience between one frame and another. And you can then decide, well, okay, I want to take a picture that's has a 300 nanosecond time delay between it, and I know I'm going to get a 95% contribution in frame 1 on one side of the image and a 5% contribution of frame 2 at the same time, and you can figure out then how much sort of crosstalk you're going to have between your images. So this is why I was talking about the electronics before, because it physically takes time to transfer your charge from your pixel into the buffer. But we can, with a gated camera, you can then actually set it so that you are then exposing your sensor to light just before this point and then just after this point of this 100 to 300 nanosecond window, and have this really short time frame, which you can't have if you're just taking an image with just an sCMOS sensor on its own. So we will talk about in the demonstration video Nicholas and I have put together, we'll actually talk about how you can use your own camera with just like a light to actually map out the interframe gap, because you can use gate mode to gate and take a series of images while still in PIV mode, and then you can map out this interframe gap and actually see on your particular camera what the transition point is and where it sort of comes at time wise. So I won't think on that too much longer. So another consideration with PIV is obviously the phosphor you choose. Given that, if you have a P43 phosphor, you have a decay time to 10% of about 2 milliseconds, whereas P46 we're in the 200 to 400 nanosecond regime. And just to sort of emphasize this, if you imagine that you went and you tried to do PIV for P43 and you tried to go for a short time scale, you're going to get a lot of sort of crosstalk between your two images, because you're going to have your phosphor decay still carrying on well into your second frame, and obviously it would actually be worse than I've sort of depicted here. So, unless you're using very substantial overlap, like sort of time between your two PIV images, and you're trying to do it with P43, often what you'll find is if you try to use P43, you'll end up with maybe a relatively dark first image, and then your second frame might end up much brighter and distorted because you're then piling up the phosphor decay from both a sort of laser burst or whatever you were looking at onto the same image. Whereas if you have a P46 phosphor, which is generally better for PIV if you're really trying to get down to like the sort of really narrow timescales, this kind of overlap is much less of a consideration, and you're only really likely to sort of encounter problems with it if you're really trying to access this sort of 100 to 300 nanosecond crossover point. That's where you might still see some phosphor crossover, but if you're doing like 2 microseconds or something, you may be at far less risk of this kind of small overlap of your phosphor. And so last, I've just got a few examples of a few things to really consider if you're trying to do PIV in an experimental setup. Much of it are things that I'm sure you're all very well aware of, such as making sure you have a good idea of the gist in your experimental setup, so you can accurately isolate an event at a particular given time. But then you can also then repeatedly do your PIV experiments to replicate results, etc. In terms of sensitivity, making sure you've got the right cathode selection, of course. In terms of dynamic range, similar to a lot of the best practices we talked about before, trying to make sure you've got maybe using the minimum gain you can to then give yourself the maximum dynamic range. In terms of time resolution, obviously the phosphor choice you go with is very important. The gating, the gate width, what you go for with that. And then obviously the interframe gap, if you're trying to do really short time periods between your imaging, then really minimizing this interframe gap and then mapping out this optical transition could be a really good way of getting the most out of your experimental setup.